In this video, we're going to talk about the flux across a surface. I want to begin with a surface, like for example, this is the top half of a sphere. And then I'm going to imagine that the surface is living in some sort of vector field. These blue arrows are indicating a vector field. For example, the vector field might be a velocity field where you've got some substance that's swirling around and it's moving in different directions according to the arrows in this vector field. And what I'm trying to measure with the concept of flux is the degree to which the vector field crosses the surface. To make more precise exactly what I'm talking about, let's actually return to the two-dimensional case that we've seen previously. Here I'm talking about a curve and I have some vector field. And the question is, to what degree is the vector field crossing outwards across this particular curve? And we've seen that this line integral, the integral along the curve of f dot n ds, was going to represent our outward flux. And basically the idea was the dot product with n indicated the proportion of the field f at a particular point that was pointing normal. If the field was just tangential along the curve, then there would be no crossing of that boundary. But if we want to know, well, how much is stuff crossing the boundary, then f dot n gives us a measure of that. And it's important to note here that I'm talking about the outward flux going out of this particular closed loop that I have, in contrast to what could have been defined as the inward flux, which is the portion coming inward. So our n is defined to be an outward normal. That's going to be important in a moment. So that's the story with the curve, but it's actually the same thing when we return back to the story with surfaces. What I've done here is not put the vector field up yet. That was going to be drawn in blue. The arrows that you see here refer to the normal vectors to my surface, the top half of a sphere. That is, at any point along the surface, there is some normal vector which is pointing outwards from the perspective of the origin, and I've just gone and plotted a whole bunch of those arrows. Now, what's key here is that this surface is what we've called orientable in our previous video. And because it's an orientable surface, which means there's two different sides that I can continuously assign these normal vectors to, I have to make a choice. And so I've made this choice where the vectors are all going out from the origin as opposed to all going inwards towards the origin. And then if I put the vector field back on, where I've got now blue arrows, that's the underlying vector field. For example, it might be representing movement of, I don't know, say a compressible gas that's swirling around. And the question is, well, how much is that gas crossing the boundary in this outward direction? So if I zoom in really closely on a small portion of that surface, so I've got the small surface and I've got the normal that I've put here, then my vector field is just going to be, well, some vector. And so what I'm interested in is measuring f dot n, because f dot n is going to be the proportion of the field which is in that normal direction. If the f vector lay in the surface, if it was tangential to the surface, then there would be no crossing of the surface at that particular point. And f dot n would be 0 in that case. But generally, f dot n tells us the proportion of the field that's in the normal direction. And as a result, if I want to know the total flux over the entire surface, well, let's just do a surface integral. I'm going to say that the flux is, I just integrate f dot n over the entire surface. In other words, it's integrated d sigma. D sigma is my little element of surface area. My assumptions are that I have a continuous field f together with a smooth surface s that's being oriented in some way by the normal unit vectors. Now, as we do over and over in vector calculus, we come up with some definition that makes good intuitive sense to us in terms of ds or d sigma, but then we always had to find a way to compute it depending on the way the underlying surface or curves are actually described. So first, let's consider what happens if my surface is described parametrically as a position function of u and v in its three different components. Well, one of the things we've seen before is that a choice for the unit normal is ru cross rv over the length of ru cross rv. And so I'm going to imagine that if my surface is orientable, that I'm choosing this particular set of unit normal vectors versus the negative, which also could have been possible. Similarly, we've seen before that for a parametric description, the little element of surface area can be described d sigma as the length of that cross product, the length of ru cross rv, and then times du dv. So putting this all together, what is the flux? Okay, it's the f dot n I've substituted in the unit normal that I just talked about. And then the d sigma is being replaced by the ru cross rv, its length, du dv as well. This looks messy, but at least there's a simplification. I see that there's a length of that RU cross RV in both cases. So I can cancel that from the top and the bottom and just simplify it just a little bit more to F dot RU cross RV du dv. Similarly, I could work with implicit surfaces. I've often called these big F before, big F of x, y, z, but I'm going to change my terminology sort of annoyingly and call it little g of x, y, and z. The reason is that big F, I've got a vector field, big F, and so I don't want to confuse the two. So I'm just going to be consistent with the notation from the book here. Regardless, I have an implicit description of my surface. And then I want to find, well, what's the unit normal? We've talked about that before. It's the gradient of g divided by the length of g. Again, I'm going to choose the positives instead of the negatives here. Doesn't matter. You could do the exact same thing with a negative. It'd be okay too. D sigma we've studied before for implicit surfaces. This is the length of the gradient vector divided by the absolute value of the gradient vector dotted with p, which was either I hat, j hat, or k hat, du dv. This gives us the surface integral of f dot. Well, I've plugged in the normal vector and I've plugged in my d sigma, my expanded d sigma. Thankfully, I noticed some cancellation. The length of the gradient vector is there in both cases, so I can just cancel that off. And this gives me the final value of f dot, the gradient of g, divided out by the gradient of g dotted this p vector. Again, a computable version of our general formula.